So welcome to our office hour. Is that in focus?
Yes.
All right, so cases. So yes, you mentioned the two main applications. If we have the quotient remainder theorem, and we know n is equal to some divisor times q plus r, where 0 is less than or equal to R is less than D. The cases turn out to be either N equals, DQ, or N is equal to DQ plus 1, or keep on going, or N is equal to, well, what would that last case look like?
It would be DQ plus one. So the remainder has to be one less at least than the divisor. So plus, I don't know, R minus one, DQ plus R plus D minus one.
That's exactly right. So that's exactly right. So, these or statements always give rise to cases. With set proofs, it arises because we have a union. If we know X is an element of A union B, then we get cases. X is an element of A or X is an element of B. And it may be something a little more complicated than A or B, but the point is, if there's a union symbol, it gives rise to the or statement, which then gives rise to cases. So let's look at sort of a classic example of a couple of proof by cases from chapter 4, where we were, using this quotient remainder theorem. Um, and these will be good ones to practice on. Prove for all integers n squared plus n is always even. And then another example would be to prove for all integers n squared plus n minus 5 is always odd. Now, if these are indeed based on the quotient remainder theorem, what is our divisor for these?
For both, the divisor is 2.
Yep, so we would have two cases where either, n equals 2q or n equals 2q plus 1, right?
I have a quick question.
Mm-hmm.
So, because we're proving in the first one that it's always even and the second always odd, for both cases, for example, the first one should have both cases equal even for our proof to work.
Yep,
Okay, and the
because
second
mm-hmm.
and the second one odd. Even with the the different cases, they should still have the same output.
That's right. That's exactly right. If our argument, is here, we're making some kind of argument. We drop in n, n could be even that we're dropping in, or n could be odd that we're dropping out, but the output, it's going to be the same wish for either input, whatever that wish is, whether it's to show that something is even or something is odd. Whichever one you're dropping in, you're going to want the same wish to happen as your output.
Okay.
So these would be good ones to practice on. I'm assuming you know how to set those up, or do you need some help with setting those up? We're,
No, and I'll work through them, but yeah, This is really good. I would get confused on the output because we're going from even divisors or no remainder to a remainder. Is it supposed to change? But okay, no, this is really good.
I've got some kind of little gnat here flying around. We're gonna have a little shadow here. Go away, little gnat. My strawberries must be collecting gnats. Fruit flies. Okay, yeah. I mean, but the bottom line is you want the same wish, and the wish is the conclusion, if we wrote this as an if then, it would be if n is an integer, then n squared plus n is even. That conclusion is what you want no matter what case you are dropping into your argument as input.
Okay.
And it's the same way with the union operator. If we have a union situation where X is an element of a union, the wish is going to be the same. How we achieve that, could vary.
Okay.
Um, did I ever post solutions to quiz 9? Let me look and see if I have solutions to quiz 9. Let's see, I don't know any solutions to those quizzes posted, and I guess I don't have those solutions handy. Um, would it help if we looked at quiz 9 maybe and worked through the
Sure.
solutions? Uh,
I wanted to ask about granularity in element chasing.
okay,
I,
explain yourself.
I remember you talked about atomic elements and then so that would be
Ah,
X is an element in A as opposed to X is an element in A intersect B, for example.
okay, that's right. Okay, granularity, that's a good way to think about it, or the coarseness. The point is, if we know that X is an element of A, and X is not an element of B, there's really no breaking those down any further. I mean, you could go from, say, this statement to the statement X is therefore in B complement. Okay, that's about all you can do with that, right? But the point is, this pretty much breaks things down uh, to what I consider atomic elements. Um, X is an element of A minus B can still be broken down because we
And
have a set operator in play there.
do we use the cases to break down these expressions?
We would use um, broken down expressions to produce cases, and then usually we build back up from cases to some built up expression. For example, hang on, let me just grab, that was a pretty good quiz. Let me just grab quiz 9. I don't have that. Oh, I'm looking at the wrong class. No wonder I don't have that in that class. That's linear algebra. There wasn't a quiz 9. Okay, so quiz 9 asked, for example, to prove for all sets A, B, and C that A minus B quantity union C minus B is equal to A union C minus B. All right. And that particular proof did require that we prove subset inclusion in two directions. People were so worked up on test 3. I noticed a lot of people proved set equality when the question only required subset inclusion. But if we're asked to prove set equality, we do have two subset inclusions. to work. So if we want to set this up, no pun intended, we can, go from this way to that way. And right away, you see that, we're going to break down what it means for X to be in this big union. So if we let X be an element of A minus B union C minus B, what would be the first thing that you would think about trying to
Say,
break down?
I would look at that union operator, and then I would say X is an element in A minus B, and X is an element in C minus B.
Well, I'm almost on the same page with you. I'm certainly on the page where X is an element of A minus B is going to be there. X is an element of C minus B is going to be there, but this is our big fat OR operator.
Right, right.
Mhm.
Union. Okay.
Right?
Right.
Right
Intersect is
is
and. Okay.
right. But union, is anything that's in either, X or Y. It's kind of bigger than either one of them by itself. Right. And so we have two cases. But in each case, and this sort of addresses what you were saying before, in each case, we wish to show the same thing, namely that X is in the other set, A union C minus B. So whether this is the input to the case, from that case, or whether we're dropping this hypothesis into our argument, we want the output to be the result that X lives in this set.
Uh,
So in case one, we can suppose X is an element of A minus B, and we kind of want to maybe think ahead. What's it going to take to show that X is in A union C minus B? We might want to kind of start thinking ahead.
we
Or,
need to.
keep going.
I'm sorry. Go ahead.
No, you're fine. Go ahead.
Um, well, we know X can't be an element in B, and we need to, okay, so X can't be an element in B, and X must be an element in A.
Or in
This
C.
A
It needs,
union C.
right.
So,
So we're going to get that, right? We're going to get it that it's an A union C because we're going to have that it's an A. So we kind of work back and forth, right? Like you're looking at what you need. We're going to have to for sure have X is not in B. We're going to get that. We're going to have to get X is in A union C. Well, we're going to be able to get that too because we're going to have that X is in A. So if we want, we could say, we wish to show X is an element of A union C and X is not an element of B. That's a wish, and it needs to be clear that that's a wish so that we don't start saying stuff we don't know yet.
ah,
But certainly in this case, where X is in A minus B, we're going to be able to get certainly that it's not in B, right? But we'll be able to get that X is in A union C because it is in A or it is in C by virtue of X is going to be in A.
okay.
So you can kind of, like these aren't so complicated that you can't really kind of see how they meet in the middle.
Mm-hmm.
So, now we would just continue to break down what it means for X to be in A minus B. Uh, oh, by the way, here I should have said by definition of what?
By definition of union,
Yeah, I should have said that there. All right, good. So now we're going to break this down. So what should we say?
X is an element in A, so I guess then, so X is an element in A, and X is not an element in B.
And that's by definition of set difference, right?
Yeah.
Some people say set minus. I accept that, but I prefer. And I think even in the WebAssign, they said by the laws of set difference, which didn't make any sense to me. I mean, it's like, wait a second, how did a definition become a law? I don't get it, but whatever. But now we're really close And we can drop out of the case now and do the other case and get X and C, or we can finish this case entirely. Why don't we go ahead and do that? Because we don't usually do that. Let's go ahead and get all the way to X is an element of A union C minus B.
Okay.
So first
So
we have to get it in here.
can we just pull out A union C? Can we just reference that?
Well, let's look at what we have. We have that X is an A. How do we logically get from X is an A to what we wish? We wish that it's an A union C. Like this is a wish. This is what we have. But isn't it true that if X is in A, that the statement X is in A or X is in C is true?
Yeah.
Right? So if you need to walk yourself through it, you can say, more words. You can say, since X is in A, we know the statement X is in A or X is in C is true. That's just by definition of the or statement. So X is an element of A union C. Definition of
Union.
union. So like I said, like you can write a little more than maybe we've written in some of the notes. Write as much as you need to convince yourself that you're not cheating, basically.
Mm.
If you repeat yourself, it's okay. As long as you don't accidentally say something you don't know yet.
Uh-huh.
So we've got that X is now, in this case, this is case one, that X is in A union C. But we also have that it's not in B. And we had that just from breaking down what it meant for X to be in A minus B. So now what can we say?
So X is not an element. So X is an element in A union C minus B.
Exactly. And that's applying that definition of.
Set difference.
Mm-hmm. And so it's weird because we're breaking down kind of the same operators that we're building back up to. They're just arranged in a different order.
Uh,
Does that make sense?
It does. This sometimes these arguments are so simple and clear that they're really, really hard.
Uh-huh, it is. It's like, wait a minute, because in your mind, you can go directly from this to that,
Hmm.
right? Kind of, sort of. But you really want to make sure you break down to atomic pieces. And then as you build up to this compound statement, you do it in steps. In other words, get this part and get the minus B part. Well, we've got the minus B part, but we need to argue that X is an element of A union C part.
Uh-huh.
Hang on, I'm gonna pause the recording for a minute because my dog is marching around, which means I gotta let him out. Hang on, I'll be right back.
Okay,
Sorry.
sure.
Why don't you work on case two
Okay.
while I pause it.
Yes, I've got it written out.
You've got it, great. So tell me what to write for case two.
So I started, suppose X is an element in C minus B.
Great.
So X is an element in C, and X is not an element in B
Okay.
by definition of set difference.
Thank you.
Since X is an element in C, we know X is an element in A union C
Okay, good, good. You can go directly to that.
by definition of union. We also have X is not an element in B
Mm-hmm.
So X is an element in A union C minus B by definition of set difference.
Great. So we've actually completely worked through inside each case to completion. And then what?
So then we can say by let's see, by our cases, we see or we can conclude that X is an element in I believe it was A union C minus, or no, A
Yeah, yeah.
minus B union C minus B.
Yeah. We can include X element of A union, no, A minus B union C minus B implies X is
X is an element in A union C minus B.
great. And now our last sentence.
So I can't see the hypothesis, but I
Well,
don't know.
we've got our two sets here. So A minus B union
Uh,
C minus B.
is I suppose a subset of
Uh-huh.
X, A union C minus B. So now we have to turn around and prove that A union C minus B is a subset of A minus B union C minus B.
Yep, because we got the first subset inclusion by definition of subset. Because we started with X and A minus B union C minus B, and we showed that that always leads to X being an element of A union C minus B. So now we're going to
Oh,
go this way, you know. So we don't even have to see at the top because we can kind of see it here. We're going to
uh-huh.
start with X here, and we're going to show X is in here.
Okay. So we could say something like, suppose X is an element in A union C minus B.
Yep,
So X is an element in A union C and X is not an element in B.
yep.
And then, okay, so do we have two cases? Because X is, okay, so case one would be X is an element in A union C. But does case two get X is not an element in B?
Nope, because and is not cases. We have to
Oh,
break this down a little further to get our cases because union is what always leads to cases. The
oh,
and, which, you know, this is an and from set difference, doesn't lead to cases. We're going to need this hypothesis in both the cases that will arise because of this union. But in whatever happens, we're going to wish to show X is in A minus B union C minus B, right? In other words, we're going to wish to show that X is in A minus B or X is in C minus B. But that's our wish, okay? This is our wish. And that's my dog. So this is what we have to break down to get our two cases.
ah.
I'm going to pause again and grab the dog, and then we'll pick right back up. Okay, so are you ready to pick up to set our cases up?
Sure am.
All right, here we go. Tell me what's right.
Okay, so case one, suppose X is an element in A minus B.
Well, that's jumping the gun a little bit because we
Oh,
haven't broken X out from being an A union C yet. See what I
okay.
mean? That's what I mean. We're not down to our atomic elements yet. Let's break down this set operator called union to set up our cases.
Okay, so suppose X is an element in A union C.
Well, it's not supposed, it is. It
Oh,
already is. So,
ah,
see what I mean, right? So, since X is in A union C, what do we know?
we know X is an element in A and X is an element in C.
Not quite. It's
Or, or,
Uh-huh.
I-
And now we're ready because, it's the union that always leads us to our cases. And until we have broken that union down, we don't really see the cases. But now we see, okay, X is going to be in A. That's going to be one case, but it's still not in B. Or in the other case, X will be in C and it's still not in B because the not in B happens above where the cases get set up, you see? So that's going to apply inside both cases.
Ah,
So here's our case one. What should we do for case one?
so since X is an element in A,
Now I'm going to suppose because
all,
I'm taking my choice. I know it's it's kind of confusing. Uh, I said since here because we already knew X was in A union C. I'm saying
okay.
suppose here because I'm choosing which of these I'm going to look at.
Ah,
So suppose X is in A.
and X is n not an element in B.
Yep, we still know X is not an
Okay.
element of B. Now you can say it lots of different ways, but I'm just saying it that way just to kind of baby my reader. But you could say also X is not in B. There's different ways to say it. But the point is that's true, whether we are picking the case one or the case two here. All right, so now what do we get? And we can now start to eyeball our wish and kind of work toward our wish.
So we still know X is not an element in B. Could we say then X is an element in A minus B?
Exactly.
By definition of set differences.
Mm-hmm. And now we can go all the way to union inside the case if we want, or we could do it outside of the case. It's up to you. It's just a matter of taste.
Let's do everything in the case. I think it'll be easier for
And
me.
that way we kind of do it twice and get lots of practice.
Yeah.
All right, so now we've got that X is in A minus B. That's where we're at.
Okay. Well, how do we get to C from here?
Well, we don't really need anything about C because we've got that it's in A, that X is in A minus B. So it is in A minus B or X is in C minus B is already true by virtue of X being an element of A minus B, you see?
Ah.
So, I can put it in quotes, X is an element of A minus B or X is an element of C minus B. That statement is true because it's an or statement and we've got one part of, one component true. That's enough.
Mm-hmm.
Thus,
I see.
X is an element of, keep your eye on your wish. It's in the union of A minus B and C minus B by definition of union.
Ah, I see. Well,
Okay, now it's your turn to practice with case two.
case two, suppose X is an element in C.
Good.
We still know X is not an element in B.
Uh-huh.
Then X is an element in C minus B. So, by definition of set difference.
Uh-huh.
So X is an element in A minus B union C minus B
Yep.
by definition of union.
Yep. And that's just fine to go directly to that. This extra sentence isn't really necessary, but it kind of helps us sometimes. But this is
Ah,
perfectly fine to go from X being in one of these two sets to being in the union of these two sets. Okay. So we showed that X being an element of, we started with X is an element of A union C minus B. We showed that X being in that set implies that X is an element of A minus B union C minus B, because, we started with this, broke it into two cases, and in both cases we got that. So we showed that this if then holds. Thus,
Um,
how do we nail it finally? Remember what we're trying to show. We're trying to show a subset inclusion.
Thus, A union C minus B is a subset of A minus B union C minus B by definition of subset.
And that's exactly right. And that's a very thorough and complete proof of that problem on quiz 9.
Wow. Uh,
Good job.
Thank you. This was so helpful. I really needed this.
Well, I'll tell you what, we can definitely have another office hour Friday night. Just email me with a request, and we can do, it doesn't have to be this late. It could be earlier in the evening. Um, just email me with a request, and then I'll send around a pop-up office hour announcement, and we can look at anything that you want to look at from either, chapter 7 worksheet or the chapter 8.1 worksheet that I'm going to get posted probably first thing in the morning.
All right. That's great.
And then you'll be able to go back over all the test solutions, and if there's any problem from any of the tests, all those solutions are posted. I guess you got that announcement.
Yep.
And if there's anything at all that we want to discuss, we can do that on Friday night. Theoretically, even Saturday morning, just email me with your request, okay?
All right. Thank you. That's great.
So I hope that that's enough for tonight.
Yes, this was just what I needed. Thank you so much.
You are very welcome. Thanks for playing. Thanks for coming.
Thank you, Professor. Have a good night.
You too. Good night.